perhaps the most successful theory ever about anything, fails in its attempt to predict the amount of dark energy in the universe.
Yeah.
And it fails badly by a factor
What's up with that, Brian?
of a Google.
Wow, by a factor of
bigger than a Google. 10 to like it's like 10 to 123 or
100,
something.
Google is 10 to the 100?
Yeah.
It gets the wrong answer by the biggest amount ever in a mismatch between theory and observation.
Yeah.
Where are we with the dark energy theorists?
Well, look, what this is showing us is that quantum mechanics is incredibly successful when you apply it to the electromagnetic force, to the weak nuclear force, to the strong nuclear force. But we've long known that when you apply it to gravity, something goes wrong, something changes. This is the motivation for string theory.
So why does empty space push the cosmos apart with a whisper when our best equations insist it should roar? We didn't expect nothing to do anything, yet the universe is accelerating, as if the void itself carries a pressure that nudges galaxies apart. That alone challenges the everyday intuition that gravity, wherever you find it, pulls. In Einstein's equations, pressure gravitates too. When that pressure is sufficiently negative, more negative than 1/3 of the energy density, it makes the expansion accelerate. Empty space, with the right kind of pressure, behaves not like a weight, but like an anti-weight. Observations of distant supernovae, the cosmic microwave background, and the large-scale clustering of galaxies all agree. This negative pressure component is real, its effect is gentle, and its energy density is tiny. About 610-27 kilograms per cubic meter, roughly a few proton masses per cubic meter. Yet it dominates the cosmic energy budget. Here's the rub. The mathematics of quantum fields tells us that even nothing is restless. Every mode of every field jitters with zero-point energy. If you tally those jitters, each one contributes a half quantum of energy, and there are modes at every frequency. Add them up, and you don't get a whisper. You get a scream. The naive total is stupendously larger than what the universe is actually doing. In most of particle physics, we cure such infinities by shifting our baseline. Only energy differences matter for forces between particles, so we can subtract a constant and call it zero without consequence. But gravity doesn't play along. It couples to whatever energy is there, baseline and all. A tabletop experiment with metal plates, the Casimir effect, reveals that boundaries can change the vacuum's energy in measurable ways. That gives us confidence that vacuum energy isn't pure myth. Yet the cosmos evidently refuses the enormous value our simple sum provides. Maybe we shouldn't blame the vacuum. Perhaps what we call dark energy isn't a static background at all, but a new ultralight field slowly changing over cosmic time. If so, the pressure it exerts could be close to, but not exactly, the value expected from a pure vacuum. That possibility has a name, and models, and a rich set of predictions. The push could strengthen or weaken in the future. Structures might grow at slightly different rates. The ultimate fate of everything could range from a cold fade to a catastrophic unraveling. We've looked for those fingerprints. So far, the equation of state, the ratio of pressure to energy density, hovers astonishingly close to -1, the hallmark of a true vacuum. If gravity itself is to blame, altered on intergalactic scales, then the equations that describe the bending of starlight around the sun and the spiraling dance of binary pulsars must somehow morph without leaving a trace locally. That's difficult. The universe has done us a favor, though. When neutron stars collided and their light and gravitational waves arrived essentially together, it told us that gravity propagates at the speed of light to exquisite precision. Many modified gravity ideas didn't survive that news. The gentle push looks uncomfortably like the very thing our quantum sums got catastrophically wrong. If the effect really belongs to empty space, we're confronted not only with a mismatch in magnitude, but a deeper question of meaning. Why should the vacuum have any gravitating value at all? Physicists seek principles that make numbers inevitable, symmetries that set quantities exactly to zero, or mechanisms that drive them there. Supersymmetry once promised a cancellation of zero-point energies between bosons and fermions. But if it exists, it's an imperfect symmetry at the energies we've probed, so any cancellation would be incomplete. Another line of reasoning turns outward, to the possibility that what looks unique might be environmental. If the universe is part of a larger multiverse born of eternal inflation, different pockets of space could freeze out with different vacuum energies. Most of those would be sterile, too large and positive for galaxies to form, or too negative for the cosmos to last. In such a picture, we happen to live where the vacuum energy is small enough for complexity to grow. Before the discovery of cosmic acceleration, that argument even set an upper limit close to what we eventually saw. It's provocative. It may also be untestable, at least with present tools. And we live where we can is a thin kind of explanation if you're used to causes you can measure in the lab. There's another possibility, quieter but profound. We may have misframed what needs explaining. Quantum field theory defines energy up to an arbitrary constant. Gravity demands an absolute value. What if space-time, through a constraint or a symmetry we haven't fully appreciated, is insensitive to the vacuum's bookkeeping choice? There are proposals. Some go by names like sequestrin or unimodular gravity, where the part of the vacuum energy that local experiments compute does not curve space-time. Instead, the observed cosmic acceleration is set by a global boundary condition, an integration constant tied to the universe's history rather than to the turbulent sum of every quantum mode. In that view, particle physics isn't wrong. It's answering a different question. The roaring terms belong to a ledger that gravity never reads. What gravity responds to is the tiny residue that escapes whatever cancellation principle nature enforces. This reorientation doesn't yet hand us a number, but it shifts the problem from how do we shrink an absurd prediction by a fantastical factor to what principle selects the baseline gravity cares about, and why does it leave a sliver behind? That shift matters beyond the math. It reframes the stakes from failure to opportunity. If dark energy is truly constant, then its value is a fossil of the universe's initial conditions or global constraints, and our job is to measure it precisely and discover the rule that made it small. If it evolves, we should catch it in the act with deeper maps of galaxies, sharper supernova, and surveys of how structures grow over time. Either way, the way forward is empirical. Next-generation observatories will test whether the cosmic push has the exact uniformity of a vacuum or the subtle fingerprints of a field, whether gravity is pristine on the largest scales or hides a new degree of freedom, whether the universe's acceleration is a temporary phase or its forever state. So, why does empty space push the cosmos apart with a whisper when our best equations insist it should roar? Because our current framework holds two notions of nothing in uneasy tension: the shiftable zero of quantum fields that matters only for differences, and the cosmological constant in gravity that responds to the absolute energy density. Whether a principle, be it a symmetry, a global constraint, or selection among many cosmic neighborhoods, sets the effective cosmological constant to its tiny value remains unknown. If such a mechanism exists, it must mute the would-be roar and leave only a small, gravitating residue. That residue is enough to shape the fate of everything, and small enough to tell us we're missing a rule that binds quantum energy to geometry. Finding that rule is how we'll turn a cosmic embarrassment into a deeper understanding of what empty really means. Like if this was interesting, and hit the subscribe for more.